Okay, finally. We need to finish up Chapter 5 because there was some of the worksheet for Chapter 5 that you probably couldn't do. I'm not going to say you absolutely couldn't do it, because if you are caught up in Math 0530, then they have actually shows you how to do those problems. But we're going to go to the practice problems, which begins with exercise 3, and we may actually have already done these, but it doesn't hurt to go back and redo. So we're going to look at example 3. Just to kind of refresh your mind. And in example 3, it says an experiment in which a basketball player who historically makes 80% of his free throws is going to shoot 3 free throws, and the number of free throws that he makes is going to be recorded. So the question we have here, is this a binomial experiment? And it is a binomial experiment, and the reason that it is one, there are only 2 outcomes. He either makes the throw or he doesn't. That's all that can happen. And those outcomes are independent. If he makes the first one, it's not more or less likely that he makes the next one or the one after that. So, probability remains constant. It doesn't change from trial to trial. So then we need to identify the number of trials. How many free throws is he going to make? How many is he going to make to begin with? He's going to make 80% of his 3. So the number of trials is going to be 3 free throws. The number of successes is going to be 0, 1, 2, or 3, because he might not make any of them. And the probability of success is P, which is 0.8 for the 80%, because he historically makes 80%, which means the probability of his failing to make it, or Q, is going to be 1 minus 0.8, which is 0.2. Now, all they want us to find with this now is the mean, variance, and standard deviation. Doesn't say anything about how many free throws can he make. It says what's the probability, find the mean, variance, and standard deviation. And because it's binomial, mu is equal to n times p. The variance, sigma squared, is n times p times q. And then the standard deviation is the square root of the variance. So that's going to be the square root of n times p times q. And since we know the value of n is equal to 3, then of his 3 free throws, we expect him to make 80%. which would be 2.4. The variance of that is going to be 3 times 0.8 times 0.2, and 0.2 times 2.4, which is 3 times 0.8, is going to be 0.48. If I did my arithmetic correctly, I probably better check that. Okay. So I'm sure that I'm right on that. So then, what is the standard deviation? Well, that's going to be the square root of 0.48. What's the square root of 0.48? 0.7? Not quite. 0.693. And it will be helpful to me if you will write your zeros in front of your decimals. That way I'll look for a decimal. Because if you're in a hurry and you don't make your decimal very dark, I may not notice it. But I'm not used to seeing a number start with 0 unless there's a decimal coming after it. So if you'll put zeros in front of your decimals, that'll make it less likely that I misread your answer. So now we're ready to go to example 4. And example 4 says a probability experiment in which 3 cards are drawn from a deck without replacement, and we're going to record the number of aces. Is this a binomial experiment? Well, on first look it seems to be, because it says the number of aces, so we're counting aces, and we're going to draw 3 cards, so we have a sample size of 3, and success is going to be it's an ace, and failure is that it's not an ace. But are the trials independent? That's right. Right here. Without replacement. So P changes every time you draw a new card. Your probability of success is going to change because the trials are not independent. So the answer on that one is no. And that means even though they've given you what appears to be plenty of information, you can't work any problems with that. You have to make sure that it's not going to be dependent events. Without replacement means they are dependent, not independent. So for example 10, it says according to research, about 70% of all U.S. households have cable television. Before we go any further, is this a binomial? It says 70% of all households have cable. So, success, cable, failure, no cable. Probability of success is 0.70. And the probability of failure then would be 0.30. So the question is, are the trials independent? If you randomly select 3 households out of a neighborhood and check those 3 houses, do you think the probability that the first house has cable has any reason to be connected to the probability that the house next door has cable? You think they ask each other, do you have cable? Because if you have cable, I'm going to get cable, but if you don't have cable, then I'm not going to. No, probably not. So we do have independent trials. We have independent trials, so the value of P remains constant. So now we can look at working the problem. 70%, well, we know what P is. We know it's 0.70. And it says in a random sample of 15 households. So that gives us the number of trials. N equals 15. What's the probability that exactly 10 have cable? X equals 10. So that means we find this one by going to Binomialcdf and put in the value of N, which is 15, the value of P, which is 0.7, the value of X, which is 10, and we calculate. I think you can see it pretty well there. So we hit second and vars, which is this key and this key. Then we scroll down until we find Binomialcdf, and we hit enter. And then we put in the value of N, the value of P, and the value of X. Close parentheses. And hit enter. And I get 0.2061. Now it's actually 0.20613, so if I round it to 4 decimal places, then it's 0.2061. Okay? Now the way to write that in correct probability notation is like that. The probability that X equals 6 is equal to 0.2061.
Why is it X equals 6?
I'm sorry, not 6, 10. Thank you. Get my bonus pen here. You get a bonus point for catching it. Okay? So probability X equals 10. Now for the next one, still talking about same situation. Oh, excuse me. It says in a sample of 15 households, what is the probability, and apparently then P is going to still be the same. What is the probability that fewer than 13 have cable? What are the values of X? What about 0? Do we need 0? Yeah, because it is possible, I mean not likely with that probability, but it is possible that none of the households have cable. So X is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, which is the same as saying we're looking for the probability that x is less than, not greater than, is less than 13. Now here's the problem. If we're going to do this problem, what we have to do is we have to calculate the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3, plus the probability that x equals 4, plus the probability that x equals 5, plus the probability that x equals 6, plus the probability that x equals 7, plus the probability that x equals 8, plus the probability that x equals 9, plus the probability that x equals 10, plus the probability that x equals 11, plus the probability that x equals 12. That's 13 problems to work. That's a lot of problems. Does anybody want to work 13 separate problems and add up the answers? Doesn't sound like much fun. Imagine if you had to do it with the formula and not the calculator. Yeah, that would really suck. Okay? So, fortunately, your calculator's pretty smart. But it's going to depend on how smart you are about telling it what you want it to do. So what I want to explain to you is what this command does. This is binomial CDF. Okay, not PDF. CDF. And what binomial CDF is, it uses the x values whatever the number is we put in last. 13, 12, 10, whatever we tell it. In this case, we know that the last number, the highest number, is 12. So even though this says less than 13, we want to add up 0 through 12. We don't want to include 13. So it's going to use the values 0 through 12, and it's going to add up. It's going to add up all the probabilities. Okay? Now I'm going to have you do this. We're going to go second. Oops, we're going to turn it back on. It's on top of it.
What's the difference between
CDF adds them up. PDF does one. Okay? I'm going to show you the difference here two different ways so you can see what it does. So here, I'm going to use binomial CDF. This is what I want y'all to do. Second bars. Scroll down, not to PDF, but binomial CDF. Okay? Binomial CDF. Trying to get this thing to focus better. Choose that. Your arguments are the same. Binomial CDF. not PDF, CDF. But your value of N was 15, because it was 15 households. Your value of P was 0.7, because 70% of the households had cable. But the number you're going to put in is going to be 12. The highest number is 13, but 13 is not included. So the highest number we need is 12. Now I want you to get that answer. Okay? Now I'm going to move this, and I'm going to use the other calculator. And I'm going to do this. Second, distributions, binomial PDF, 15, 0.7, 0, plus again 15, 0.7, 1, plus 15, 0.7, 2. Finally, I have entered in every one of the binomial PDFs, and I'm going to hit enter. Do you see what it did?
Same thing.
The same exact thing. Which way do you want to do it? Binomialcdf, right? Okay.
So why are we not always use CDF? We use CDF for the long call.
It will give you a wrong answer. It will give you a wrong answer. The difference between the two is that Binomialcdf calculates one single probability for one single x value. Exactly 10. Okay? X equals 5. Okay? When it says no more than, no less than, fewer than, greater than, equal to or less than, at most, it doesn't say exactly or equals to. Then you go to Binomialcdf. But you have to be careful. So I'm going to try to explain this so that you won't get it mixed up. This one was 0.8732. Now, the next one sounds very, very, very similar. Come on, scoot over. 0.8732. Regardless of which way we did it. There's the long way. And then the short way is that way. Exact same answer. Just depends on how hard you want to work to get the answer. So remember, this one was fewer than 13. When we look at the next one, it doesn't say fewer than 13. This one's still a random sample of 15. What is the probability that at least 13? How many is at least 13? 13 or more. So here's what I want you to pay attention to. That is all the possible values for x. Okay? That's all of them. Fewer than 13 is all of those. At least 13 is all of those. What do you call this and this in statistics language? What's the definition of a complement? Either the sun rises or it doesn't. The probability the sun rises plus the probability the sun doesn't rise is 100% because it's either or, but the sun doesn't rise is the complement of it does rise. We're going to have a test on Monday. What's the complement? We're not going to have a test on Monday. Okay? Compliment is either you are or you aren't. Stop looking so shocked, Nick. I didn't say we were or we weren't. Okay? Fewer than 13, at least 13. Now, there's two different ways to do this problem. Since you know that x is at least 13, which means x is equal to or greater than 13, you could find probability x equals 13, 14, 15 by just calculating 3 probabilities, which is not so bad. It beats the heck out of what I did in calculating 13 of them. You could just actually add up the probability that x equals 13 plus the probability that x equals 14 plus the probability that x equals 15, which is actually what the answer is. But you still have to do 3 different things. There are either at least 13 or there's not at least 13. The probability x is equal to or greater than 13 is 1 minus the probability that it's less than 13. Okay? So in order to find the answer to this problem, we use the same probability we did last time, except we're going to subtract it from 1. And it's 0.1268, and that's it. Yes?
What is the edit for?
What is the
F.
F at the end here?
No, just like in general F. Like I know Q stands for like the failure, it's like 30%.
Okay, F is the failure to have cable television, so Q would be 1 minus 70%, which would be 30%, 1.3.
What's the difference between F and Q? 'Cause on the homework like last time.
F is the
Q
actual.
and F.
F is the actual failure. What do you consider failure in this case?
So it's like it's a word.
It's a word.
Okay.
Okay, success in this case was has cable. Failure was no cable. Okay? Now I'm going to warn you. If you can't figure out how to do this, then please just do the individual probabilities and add them up. Because you have to figure out how this works. Some people can, some can't. We're going to practice. But the thing that's going to trip you up the worst, if you're not careful, is that you can't remember what greater than, less than, fewer than, and all that is. So what I'm going to do is I'm going to pull up something right now. We're going to do a little impromptu quiz. Whole class together. was not what I was looking for. I didn't name my stuff very well. And I want you to go through these with me as a group. Just look at these. I will post it in Shelby if you want to practice later on, but let's look at these as a group. The first one is the original statement. X is greater than or equal to 6. In symbols, that would be X is with the inequality sign equal to or greater than 6. What is the complement of that event? If it's not equal to or greater than 6, then what is it? It's less than 6. X is less than 6. Okay? Does 6 work in the original statement? Is 6 included in the original statement? Yes. That's where the equals comes from. Okay? X is different from 6. How would you write that in symbols? That's the equal sign with the slash to it. This is not going to be in the recording, so I'm going to pause. You can do this because your calculator does this, but you have to know what numbers to put in. Okay? You have to be able to figure out what that last number is. And sometimes you have to say 1 minus that last number. So let's practice a little bit more. Then we'll take a break and do chapter 6. We won't finish chapter 6, but we will get started. Okay, so we're looking at example 6. Example 6 says, according to crime in the United States, 1998, about 60% of murders are committed with a firearm. So suppose we went into the crime statistics and we randomly selected 14 murders, knowing that 60% of those are committed with a handgun. I want you to identify success, failure, number of trials, probability of success, probability of failure. What is success? When we gather our information and we look at the outcomes of the 14 murders, what are we counting as success? Murdered with with a firearm, okay? Remember I told you success isn't always a good thing. Success is murder with a firearm. Okay? What is failure then? No firearm. That's all the other ways. Strangled, drowned, suffocated them with a pillow, chopped them up in little bitty bits, dropped them in cement. You know, there's lots of ways to kill people that don't involve firearms. And that includes all of them. All of them. How many trials are we looking at? 14. What is the probability that any one of those 14 murders was committed with a handgun or with a firearm? 60. 60%, which we'll use as a decimal, 0.6. Then what would Q be? What's the probability they weren't committed with a firearm? 0.4. Now, it is true, I want you to understand up front, I know that you really only need to know what this is, because if you know what that is, you've got to know what that is. But to do the problem, all you need to know is this and this. But you should be able to identify all of those. And then in the next problem, what does that give us? What is the probability that exactly 13 murders are committed with a firearm? What have they told us? What is the probability that exactly 13 out of 14, exactly 13 murders are committed with a firearm? What is X? 13. What does this tell you? It equals 13. Okay? And anytime it's equals to, it's PDF. Now, I'm not going to work the problem for you. I'm just going to fill these out. I want you to go back in and fill the numbers. But I'm telling you exactly how to work them. Next question. Find the probability that eight or more murders are committed with a firearm. What is X? I mean, actually show me what X looks like. So, what are the values of X? Not symbols. What are the numbers? Do you include 8? Okay. How do you write that in symbols? Okay. Now, remember, this is very important. Write this down. Binomial PDF means x equals. And that's it. Nothing else. Equals. Binomial CDF means that x equals this going up to some ending number. Okay? So this is actually x is less than or equal to the end. Whatever that last number is, that's what I'm calling end. Is that what this is? This says equal to or less than the end. This says equal to or greater than. Is that what this is? What is it? What we call the complement. Okay, this is the complement. So this is going to be 1 minus binomial CDF 14, 0.6, but what's the end? What's the last number I need to add up? That's the complement of this. What's all of the numbers 0 through 14 that are not equal to or no, all the numbers 0 through 14 that are not greater than or equal to 8. What is the complement? Or, okay, go back to the sheet we were doing a minute ago.
0 through 7.
0 through 7. Okay? This is x. This is how we write it. The complement is 0, 1, 2, up to and including 7. Not these. This is the complement. The complement is x is less than 7. That means the end is 7. We only accumulate from the bottom, not from the top. When you accumulate, you start here and go to the top, to the end. So when we accumulate, it always starts at 0 and ends here. If we need to start at 8, we can't do just this. That's when we have to use the complement rule and subtract it from 1. Okay? You've got to learn to think about what the complement looks like, because the complement is what you're actually going to find the probabilities for and then subtract from 1. Anytime you've got a greater than or equal to or a greater than, you have to use the complement. 1 minus Binomialcdf. That's the way you're going to have to do it. If it says this or this, you're going to do 1 minus Binomialcdf. And then based on whether it's this or this, you need to figure out what that last number is. What's the last number you want to add in? Where's the top? Where does the accumulation end? It always begins at 0. Where does it stop? When you've got greater than or equal to either one. 8 or more, that says greater than. Higher.
Notice where the count the number is below the number, like it says 8, count 0 to 7.
Right. The only thing you need to worry about is 8 included here or is it included in the complement? And that sign will tell you which way it's included. It's included in this, not in the complement. So that tells you the complement ended at 7. Okay? This is the part where y'all are going to have to practice. Okay, let's look at this one. What's the probability that 4 or fewer? What does that look like? What is X? Is 4 included? Yeah, it says 4 or. Less than or equal to 4 because fewer tells you you're going down. Okay, because it's less than, or if it's less than or equal to, you don't need the 1. You just need binomial. N is still 14, P is still 0.7, 4 or fewer, add up 0, 1, 2, 3, 4. 4 is included. Now if you'll actually write these out this way, it will help you. But if you go through doing your homework and try to memorize rules, just write down the answer. That's what you're going to do on the test. And I can't give you credit for what you should have been doing up here if you don't put it on paper. Write it down. I will count off if you don't use correct probability notation. If you just write down a number for the probability, you just answer the question. Or just put, P equals. Nope. You're not going to get full credit. You might have the right number. You'll get some points for having the right number. But you need to write what the answer is. If you want complete full credit, you're going to write all of that. Because if you don't, you're going to make a mistake.
Do we have to write out the final too?
Yes. Because that way I know what you put in. I need to see enough of this to know how you did this. So let's say this was a problem on a test. And, you put down the answer. Okay. 1 point. 1 point. 1 point. 1 point. 1 point. Any piece you leave out, you lose 1 point. Because if you don't write this, you're not going to get this right. Yes, Nick. 70. Oh, I'm sorry. That's my bad. Sorry. Plus 1 for Nick. That look better?
Yeah.
Because it's 60% are with handguns. I'm focusing so much on making sure you do the rest of it right, I wrote the wrong p-value.
So pretty much nothing changes on the PDF except for one number. You're changing one number every like question.
Mm-hmm.
Okay. You're always gonna have 14 and 26 in every answer you give.
Exactly.
Okay.
Because that's in the setup for the problem. Okay, let's do a couple more. Make sure you got it right. Find the probability that between 10 and 12 murders are committed with a firearm. Between 10 and 12. If it doesn't say inclusive or exclusive, which this one actually should, I hate that it's not worded better than this, you always assume that it's inclusive. Assume that it's inclusive. Now, if I assume that it is inclusive, what does that mean the potential values of X are? 10, 11, 12. Can you use Binomialcdf to do that one? There's more than one. But I want you to think about this. That's all the possible answers. Well, back out a little bit. There's all the possible answers. There's the ones that I want. Now remember, Binomialcdf would be that. If I said more than 12, that would be 1 minus. I have no way to tell it to start at 10. It only starts at 0 and goes up. That's all this does. Starts at 0 and goes up. If I take 1 minus, it starts at the number 0 and goes up, and then subtracts the result from 1. Can I use either one of those on that? No. So what's the only way I can do that problem? You got to do PDF and add them up. So that means you're going to have to do Binomialcdf 3 times. And that's the way you write that. That's the probability notation for it. And the thing that I want you to notice here is that any time x is between two numbers, if x is in the middle and there's two numbers on the outsides, the signs always point to the left, because the beginning is always smaller than the end. So if you just leave x out completely, is 10 greater than 12 or is it less than 12? 10 is less than, therefore you have to point your signs to the left. You never point them to the right. It's always to the left. Okay? And we're going to do one more. Find the probability that exactly 10 murders are, this is the important word, not committed with a handgun. It says exactly 10. What's changed? Yeah, you're going to use Q instead of P, because success now is not committed. They've changed the qualification for what success is. They've made failure into the success. And that means you're going to use Q, not P. You're going to use 1 minus 0.6 because the probability they're not committed with a handgun is 40%, 0.4. Okay? Watch your wording. I've said this from the beginning of chapter 4. The biggest part of probability that trips people up is they don't read carefully. Read very, 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 very carefully. Make sure you understand what it's asking. Don't overthink it, but make sure you know what the question is asking you. Okay? Now I'm going to leave you to finish that off for homework, plus the rest of the 2 worksheets. I've extended the due date on the worksheet. And I'll do example 7 and post the entire page of example 7 completely worked out for you. But I want you to try it before I post it. So I want you to try this before Wednesday and make sure that you can do these. Because example 7 puts together everything that we've done so far. So I want you to get some practice.
What, finish all the worksheets?
Finish the other 2 worksheets. You have 2 problems left on the other 2 worksheets. You could have done problem 1 on both of them, but you probably couldn't completely do problem 2 because they were the ones that asked about CDF, using the CDF. So you've got time to still work on those other 2 worksheets. Plus I want you to finish this. I want you to put the numbers on this one. And if you're not sure of a number, ask a question. But I mean, I've told you exactly how to get the numbers here. I want you to try your hand at this one. Show me all the work. I want to know what all the work looks like before I have to grade it on a test. If you hand me this with a bunch of numbers on it, I'm going to put big old, let's see, 1, 2, 3, 4, 5, 6, 7, 8. You get a whole 8 out of this. This is example 7 on the notes. So I'm going to give you 8 points if you write down the right answer. You miss any of it, then of course it's going downhill from there. But in truth, this worksheet is going to be worth 25 points. This exercise is the last page of your notes. The very last page of your notes, example 7. This is worth 25 points on a daily grade. That means you need to write down the probability x equals, or is equal to or greater than, or is less than, or is greater than, or whatever. You need to list out the values of x, and then write the binomial CDF that goes with it. That's the points. Numbers, yeah.
The whole thing going uploaded and showed?
Yeah, just this one page. Just this one page. The rest of it's for you. And then I'm going to post the answers exactly the way I want to see them. But I'm not going to post them until everybody's put theirs in the folder. So get this done by Wednesday. I need to know if you've got this. I don't like finding out on tests you didn't get it. I want to know now you didn't get it so I can fix it. Now, I told you, I scared Nick, that the test would be Monday. And I had sort of planned for it to be Monday. But I think I'm going to put it off until Wednesday. We are going to have a test 1 week from next class period. We are going to start chapter 6 right now. How many people did not print off the chapter 6 notes? Did you do your notes on Shelby or on paper?
No, what I did, I'm sorry.
You did print them off?
Yes, I did.
Okay, you need to get your chapter 6 notes. We're not going to get finished, but we are going to start. The chapter 6 notes look like this. We may not get very far, but we're going to start. On your computer or your iPad, go to nearpod.com. This is your code. Get logged in. Now, if you like to take your notes on your iPad, log into Nearpod on the computer and then have your iPad open and show you. If you want it pencil and paper, just log in on the computer or your iPad, either one. On the iPad, you can use the app. What we're going to talk about in Chapter 6 is something called normal probability distributions. This is not in the notes, but I'm going to try to lead you from Chapter 5 into Chapter 6. Chapter 5 was about discrete probability distributions, which means that the random variable can be counted. Murders that were committed with a handgun, people that had successful surgeries, people that made free throws, 1, 2, 3, 4, 5, 6. Okay, there was nothing between 0 and 1, nothing between 1 and 2, nothing between 2 and 3. Normal probability distributions applies to a lot of what we see in real life. The difference is that the random variable here is not discrete. It is a measurement, a height, a weight, a volume, a net weight of a bag of potato chips, all kinds of different things that are either naturally occurring around us or actually manufactured by human beings, or information about human beings, such as the weights of newborn babies or the heights of 4th graders and things like that. So here's some basic information. And if you've gotten through this chapter in 0530, this should look a little familiar to you. Okay? The properties of the normal probability distribution. The curve is bell-shaped. We're always going to do normal probabilities on the calculator, and we're always going to look at a graph. We're never going to make a table. There will never be a table for normal probability distributions. If you see a table, the table tells you it's discrete. Because in normal probability distributions, we can't list all the values of x because they're measurements. So we're not going to be using tables. We're going to be using a formula, which your calculator already knows, and we're going to be using pictures to make sure that you're doing the formula right. Okay? Now these are the characteristics of any normal distribution. One of them is that the curve is bell-shaped. Bell-shaped means it's got a high peak in the middle and it kind of trails off on both sides and flattens out. Its highest point is over the mean, which is mu. The mean of the distribution, the mean of the population, is in the very center of that curve. It is symmetrical because the mean, the median, and the mode are all three in exactly the same place. They're all right there in the middle. The second property is what I just told you. The curve is symmetrical. It's symmetrical around a vertical line drawn through the middle where mu is. Its left half and its right half are mirror images of each other. The area under the curve represents probability. It is a probability graph, and the area under the curve is the probability. Very important thing to realize is that even though if you look all the way up at the upper right and all the way down to the lower left, it looks like it comes down and touches the x-axis, but it doesn't. It approaches the x-axis, the horizontal axis, but it never touches it, it never crosses it. That means the upper bound for the probability distribution is infinity. And the lower bound for the probability distribution is negative infinity. The curve goes on forever, literally. But the area, the further you get from the center, gets smaller and smaller and smaller until it's almost zero. The empirical rule applies to any symmetrical and bell-shaped distribution. There is another symmetrical distribution that is not bell-shaped. That other symmetrical distribution is called a uniform distribution, and that distribution is just flat. For example, if you were to draw the probability distribution for rolling a six-sided cube we call a die, since all the probabilities for all the various numbers are the same, 1/6, then its graph would just be flat across the top. And that would be called a uniform distribution. This is the empirical rule. Part of the empirical rule is where we got the range rule of thumb. We've had the range rule of thumb since chapter 1. Part of that rule actually comes from the empirical rule. What the empirical rule says is that about 68% of the data values will be within one standard deviation of the mean. So basically you expect about 2/3 or a little better than 2/3 of the random variable values to be within one standard deviation above or below the mean. If you take the mean minus one standard deviation and the mean plus one standard deviation, that will give you an interval where 68% of your possible values for x are going to be. If you go out an additional standard deviation, if you go down from the mean minus 2 standard deviations and up to the mean plus 2 standard deviations, that interval will contain 95% of all of your random variable values. This is the part that gives you the range rule of thumb. The range rule of thumb says that anything that will lie outside of the mean minus 2 standard deviations to the mean plus 2 standard deviations, we consider that unusual. Well, the reason it's unusual is because 95% of the time your values should be in that interval, which means 5% of the time or less they're going to fall outside that. And if the probability is 5% or less, we consider that to be something that's unusual if it occurred. Now it goes one step further. It says virtually all of the distribution will be within 3 standard deviations of the mean. So if you had a value that fell more than 3 standard deviations below your mean, that would be highly unlikely. The probability would be nearly 0. For all intents and purposes, we would say that it is 0, because it would be half of 0.3%. And half of 0.3% is 0.15%, 15 thousandths probability. So almost all, 99.7% of all of your values of x are going to be on the interval, the mean minus 3 standard deviations to the mean plus 3 standard deviations. So now we're going to do an example. And I'm going to stop out here and actually do the example with you. The example's in the middle of my page here. It says the life of a particular light bulb is normally distributed with a mean of 1,100 hours and a standard deviation of 100 hours. What's the probability that a light bulb of this type would last between 1,000 and 1,200 hours? Now, what you're going to want to do, and you're not going to be very good at this at first, I promise you're not, but you will get better, and on top of that, I will put a sheet of normal curves you can print out so that you don't have to draw them, you can just label them. But what this is telling us when it says normally distributed, it means that those light bulb lifetimes fit on a normal curve. Which means it's going to look like that. It says the mean is 1,100 hours. And it says the standard deviation is 100 hours. So if I go up one standard deviation, 1,100 plus 100 is 1,200. And if I go down one standard deviation, 1,100 minus 100 is 1,000. And that just so happens to be what they asked us about. What's the probability that a light bulb of that type will last between 1,100 and 1,200 hours? Well, this is the mean plus one standard deviation. This is the mean minus one standard deviation. And the empirical rule that tells us that the area under the curve between those is 68%. So the probability that that light bulb is going to last between 1,100 and 1,200 hours, I'm sorry, 1,000 and 1,200 is going to be approximately equal to 0.68. Just by looking at the picture. Okay? So the arithmetic behind this is that we went, well, 1,000 minus the 1,100 mean is equal to negative 100, which is one standard deviation below the mean. And the 1,200 minus the mean is 1,100, is 1,200 minus 1,100, that's 100, which is a positive one standard deviation above the mean. Positive means it's above. And since we're talking about one standard deviation below to one standard deviation above, the probability is about 68%. Now, you didn't do any calculations for that. That is strictly an example of the empirical rule. You didn't need to really do any arithmetic. If you drew a picture of what the light bulb distribution looked like, you wouldn't have to do any arithmetic at all, hardly. You could just look at it at your labeled picture and say, well, I know the answer because the picture says this is within one standard deviation. Now here's one, you don't have to be able to do this. Do not grab a calculator. Use the picture that I just showed you. Use the picture and answer the question. The life of the light bulb is normally distributed with a mean of 1,100 hours and a standard deviation of 100 hours, which is the picture I just drew. What's the probability that the light bulb is going to last between 900 and 1,300 hours? Add some numbers to your chart. Remember, the standard deviation is always the same. And then use your chart to answer the question. Click submit and wait. I'll know you submitted it because I'll be able to see your screen says great. If you don't click submit, I'm not going to have your answer, and when I print out the report, I'm not going to know you were here. Because that's how I'm taking the class roll when I do a Nearpod, is I print out the results of the quiz that it does, and I use that to check the roll. And you do get a quiz grade for it. Even if you're wrong, because I drop a certain number in Nearpod quizzes, but I mostly use it for attendance. Nearpod quizzes usually like 1 or 2 points. They're not a big deal. I think everybody's answered. So if you did what I told you to, 1,000 minus 100 is 900. 1,200 plus another 100 is 1,300. The question was, what's the probabilities between 900 and 1,300? And the empirical rule says that's 95%. Which would have been answer B. Okay? And I've hidden your name so you don't know who's who. And in case you're interested, no, they are not in alphabetical order. They're in the order that you joined the presentation. So you can't figure out who you are on that list. Now, the only other part that we're going to worry about today is talking about something called a standard normal distribution. A standard normal distribution always has a mean of 0. And it always has a standard deviation of 1. All of your x values are converted to z-scores, and a z-score looks, a z-score is not listed on the PowerPoint, but I'm going to show you how to find a z-score. The z-score formula is that formula right there. And what a z-score tells you is the number of standard deviations between the original measurement and the mean. And just for example, you might want to add this to your notes here. This z-score is 1. And the reason it's 1 is because it's 1 standard deviation below the mean. And the z-score for 1,200 is also 1 because it's one standard deviation above the mean. The difference is that this z-score is actually -1. And the negative tells you it's below. So all your z-scores to the left of the mean are negative. All your z-scores to the right of the mean are going to be positive. And the z-score of the mean is going to be 0 because it is not any different from the mean. It's at the center point. It's going to be 0. For anything else, you use z equals x minus the mean divided by the standard deviation. Okay? And I'm just going to hop on down and do these two examples with you. Convert 21 minutes to a z-score. It says that the mean for the pizza delivery time is 25 minutes. And the standard deviation for the z-score time is 2 minutes. And it wants you to convert 21 minutes, which is an x value, to the z-score. Z is equal to the x value, 21, minus the mean, 25, divided by the standard deviation, which is 2. 21 minus 25 is -4, divided by 2, and that's -2. So that tells you 21 minutes is 2 standard deviations below the mean. In other words, those people are slow. They're bordering on getting fired because that's pretty far away from the mean.
Below the mean,
You know it's going to be a negative. That's exactly right. Okay? If it's 29.7 minutes, this is the last one we're going to do. The z-score for 29.7 is the x value, which is 29.7, minus the mean, which is 25, divided by the standard deviation, which is 2. 29.7 minus 25 is 4.7, divided by 2, which is 2.35. So they are 2.35 standard deviations above the mean. They are really fast. They're pretty far from the mean, but these delivery guys are fast, so they might get a bonus. Okay? If you can deliver it that fast, then that's a lot faster than the normal time. You should get a good tip. Okay? We will pick up there using the same code next time. And I will see you on Wednesday.